Okay, can I move on?
Yeah.
Okay, I'm going to do a practice problem where we combine some things, then you have to decide what the predominant redox reaction will be. And this is really easy to figure out. You look at the strongest available oxidizing agent and the strongest available reducing agent. It's kind of logical. Okay, turn to the next page. And it's all based upon where are they arranged on the periodic table. Okay, or not the table, but the SRP table. So turn here to the practice problems. And let's take a look at number 1, okay? So here it says, write the predominant redox reaction that will occur in the following mixtures. Okay, look for the one that's the top left, on the top left of the table, and the one at the bottom right. And that's our winner. You tell me.
I feel like one of them's broke. I lied to you guys.
You got something higher than that, I think.
If I can make it up.
It's hard because it's so small.
They really don't care about your feeling ice. Yeah, that's what
Buying
Eyeballs.
They just said something about the music directors.
SN plus 4.
Yeah.
Okay, and then bottom right, NI, good call. Okay, so these two are the winners. We don't care about the other ones. So since SN plus 4 is in the top left, we're going to write that half reaction as it is in the order that it's written. So we have this, and then we have to reverse the order of this half reaction. So this is going to be Ni going to Ni plus 2 electrons. And when you add these together, the electrons cancel, and then what you have left is the predominant redox reaction. Piece of cake? Mm-hmm. Awesome. Let's talk about redox titrations. This is what we're going to do next week. This is the 2-day lab. Okay, let's come down here. Yikes, too far. Okay, so what you're going to do is you're going to be titrating an oxidizing agent with a reducing reagent, or vice versa. And you have to choose a titrant that's strong enough of an oxidizing agent to react with the reducing agent, or the other way around. Okay? Now, the indicator of acid-base titrations is typically a weak acid with a different color when it turns into a base. So the indicator of a redox titration is a reducing agent with a different color in its oxidized form. Okay, so typically we choose a redox indicator that's a weaker oxidizing or reducing agent than the analyte that we're looking at. So that way it can be completely consumed. And then let's come down here. Purple permanganate is sometimes used as an oxidizing agent to titrate with. What happens is the permanganate ion is reduced to a very faint pink Mn plus 2 under acidic conditions. I recommend you earmark this page so that you can refer to it when you're doing the lab. Okay. When the permanganate solution is slowly added to a reducing agent of unknown molarity, the permanganate ion is reduced and the purple color disappears. So eventually you add a drop, the purple color remains, and at that point you know that whatever was reducing the permanganate has been completely consumed and you've hit the equivalence point. Okay, so take a look at the practice problems on the next page. We're going to take a look at practice problem number 1, A, B, and maybe number 2. So let's come over here. Here it says potassium dichromate is used to titrate iron 2 chloride. Dichromate is its own indicator. The orange dichromate is reduced to green as it oxidizes the iron to Fe+3. The equivalence point is evident when the orange color remains, indicating that Fe+2 has reacted. So here you've got 15 milliliters of 0.02 molar dichromate, and we're titrating 20 mils of acidified iron 2 chloride. Balance the redox reaction for this titration. To save us time, are you okay with me just giving it to you?
Yeah.
Okay, so this is going to end up being 14 H+1 plus Cr2O7 plus 6 Fe+2, 2 Cr+3s, 7 waters, and 6 Fe+3s. Okay, so I've got 15 mils of this at 0.02 molar, and then I've got 20 mils of this, and I don't know what the concentration is. Okay. Follow the same format as we have in all the other titration calculations. So you start here where you've got a molarity and a volume of a substance. So take your 0.02 molarity times 0.015 liters. This will give you your moles of dichromate. Okay. It's 3 times 10 to the -4th. Then you have to do your mole ratio. So you've got 1 dichromate for every 6 iron 2. Okay, and then we're going to divide it by 1/0.02 liters of iron 2, and this is going to give you your molarity. Okay, I don't think we need to do number 2. It's the same sort of setup. Yes, Jules.
So if you're trying to, let's say like we don't have the whole FeCl2 compound, we just do the ion that there's one of.
Yes.
Okay.
Okay, now let's turn to 7.4. Did you guys do a battery lab at all? No. Okay. You good?